So I'm going to solve problem number 9. It says that if a system of linear equation ax equals to b has a unique solution where A is a m cross n matrix, then m equal to n, which is clearly false. In particular, you can choose, say, m to be 3, n to be 2, and consider the matrix A to be 1 0 0 0 1 0. Okay, then if you multiply it by the vector xy, you will get x y 0. Now in this case, if you choose b to be the 0 vector, then you will see that the solution is exactly the 0 vector itself. Hence the solution is unique, but m not equal to n. Hence clearly this option is false. Option Q. W inside V is a subspace. Okay. Given that U belongs to V minus W and V belongs to V minus W, this will imply U plus V also belongs to V minus W. So C, choose any vector x belongs to V minus W. This will imply minus x also belongs to V minus W, because minus x belongs to V minus W, it will imply, because minus x belongs to W implies x belongs to W. W is a subspace, right? So since W is a subspace, minus x belongs to W implies x belongs to W. That means either x and minus x both are not inside W or both are inside W. So I can choose some vector x such that x is not belong to V minus W, as well as minus x also doesn't belong to V minus W. Okay, I mean, not doesn't belong to, I'm assuming that x belongs to V minus W as well as minus x belongs to V minus W. That is obvious, we can choose that because either x and minus x both are in W or both are outside W. Okay, then by the given condition, x plus or minus x, which is 0, belongs to V minus W, which is a contradiction, because since W is a subspace, 0 is always inside W, so 0 cannot belong to V minus W, hence this is false. So both the statement P and Q are false, so option D is correct. Question number 13. Let V be a non-zero subspace of M7C such that every elements of V is invertible. Okay. Then you need to find out dimension of V over C. Okay. So see, if V is spanned by a single matrix A, okay, if V is spanned by a single matrix A where A is invertible, then we are done, right? Because any element here is basically looks like this. Any non-zero element here is, if you can take this, that will give you identity. Hence any non-zero elements in this subspace is invertible. Hence dimension is 1. So hence for dimension 1 it holds, that is true. But is it always true that dimension will this condition will imply the dimension 1. So proof. So if possible, there exists a B belongs to V such that B not equal to TA for all T belongs to R. That means B is not in the span of A, which will imply that A and B are linearly independent. Okay, as a vector. Here it is everything happens in the matrix, but they are actually as a vector in M7C, right? Because we are talking about vector subspace. Okay, so in particular B not equal to TA, right? Now A plus sorry B plus TA belongs to V, since V is a subspace for all T, right? P and A inverse plus Ti is invertible because B plus TA is invertible by given condition. Okay, here it is A inverse. If we multiply it by A inverse, we will have this one. That is also invertible because B plus TA is invertible from our given condition, and A inverse also invertible because A is inside V itself. So B A inverse plus Ti is invertible for all T belongs to C. Oh, okay, sorry. Here it is not R. Here it is C because we are taking complex vector space. Okay. Now the thing is that observe the B A inverse is a matrix in M7C, right? Since so that means that BA inverse must have an eigenvalue because it is inside C. So characteristic polynomial splits, right? The 7 cross 7 matrix. So its characteristic polynomial has 7 degree 7. So there exists at least one element lambda such that BA inverse minus lambda I is non-invertible. We can always find that gives you contradiction because you can choose T to be here T equal to minus lambda particularly, right? Then it will not be invertible, which is a contradiction, which is a hence contradiction. Okay, that's why dimension of V over C is 1. Okay, 15. A is given that 1 by root 3 minus 1 by root 2 1 by root 6 0. Okay. So first of all, observe that rank of A transpose is less equal to rank of A, right? That means rank of A transpose less equal to 1. And since A is a non-zero vector, this will imply rank cannot be 0. That is obvious, right? Because you are taking rank of A transpose is not equal to 0. Hence, it implies that rank of A transpose is 1. Okay, then eigenvalues of A transpose equals to 0, 0, 0, lambda. Well, lambda can be 0, can be non-zero, anything. Okay, because rank of A transpose is 1 and the whole matrix A transpose has order 4 by 4 matrix. That means nullity is 3. So nullity is 3 means eigenvalue geometric multiplicity of 0 is at least 3. It can be 4, but at least 3. So I am assuming that the eigenvalues are 0, 0, 0 and lambda. Well, lambda could be 0 or maybe non-zero, anything. Okay. 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 Okay, again, trace of A transpose is what? Trace of A transpose is basically 1 by 3 square plus 1 by root 2 minus 1 by root 2 square plus 1 by 6 square, which is basically 1 by 3 plus 1 by 2 plus 1 by 6, which is basically 1. So trace of A transpose means sum of eigenvalues, that means lambda equal to 1. So we already have all the eigenvalues of A transpose 0, 0, 0, 1. Then we are actually done. Why? Then eigenvalues of I minus A transpose basically 1, 0, 0, sorry 1, 1, 1, 0, and eigenvalues of I minus 2 8 transpose is basically minus 1, minus 1, minus 1. Oh no, 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 no. Sorry, 1, 1, 1, minus minus 1. That means I minus 2A transpose is invertible because all the eigenvalues are non-zero, but I minus A transpose is not invertible because at least one eigenvalue here, which is 0. That means Q is true but P is false, so A is correct. Okay. Question number 17. So P11x is a real vector space of polynomials in variable x with coefficient having degree at most 11. Okay, so here E is given by S0x, S1x, S11x. Okay, and S0, S1, S2 all are some polynomials. Okay, similarly, and that satisfies some condition that S03, S13, S113 is 0. Similarly, for F we have R0x, R1x, and so on. Okay, so let me do so. So I write down since it is a degree 11 polynomial, at most degree 11 polynomial. So I write down skx as a k1 x, sorry, a k1 plus a k2 x plus dot 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 a k12 x to the 11. Okay. So in particular, if I write down s0x, this problem could be slightly lengthy. Okay, a0x, it starts with 0, right? Okay, so then this will not work. Okay, so let a0x is basically a11 plus a12x plus dot 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 a112 x to the 11. S1x is basically a21 plus a22x plus dot 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 a212x to the 11. S2x is basically a31 plus a32x plus dot 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 a313x to the 11, and so on. Okay. Okay. That means if I write it as a matrix form, what will you get? It is a 12 by 12 matrix. Here a11, a12, a112, a12, a12 times 1x x squared x to the 11, which is basically same as s0x, s1x, s11x. If I write it as a matrix representation. Now it is given that s03, s13, s113 all are 0. That means I can write it as this matrix. Say it is a times 1 3 3 square 3 to the power 11, that is 0 0 0 0. Now observe that A sends one non-zero vector to a zero vector. That means columns of A are linearly dependent. Now observe that the linear independence or dependence, whatever we are going to do, we are doing basically it with the with the coefficient, right? We are interested in coefficient because 1x x square so on x to the 11th forms a basis. So we are basically interested about its coefficient and we are computing it and we are trying to check that whether it is linearly independent or dependent. Okay, so exactly it comes in from this matrix. So since columns of A are linearly dependent, that means any such any such E is linearly dependent. Okay. Any such E is linearly dependent. But similarly, if we do it for R, okay, if you do it for R, then the same thing will happen. Okay, and there is a same thing will happen. And if I write it that matrix as B, then we have what we have. Yeah, we have B 1 4 4 square so on 4 to the 11 is basically given by 1 1 1 1 1. So from here we can't conclude because it might happen that that we can choose some matrix B such that B is linearly, so the columns of B is linearly independent, but it sends this column vector 1 4 4 square so on to one vector. As an example, you can take B to be say 1 1 by 4 1 by 4 square 1 by 4 to the 11, the diagonal matrix, not diagonal but I mean the square matrix, sorry, the diagonal matrix. Okay, and then if you multiply B with the column vector 1 4 4 square so on to the 11, you will get that. That means in particular if you choose F to be say 1 1 by 4x 1 by 4x square 1 by 4x to the 11, you can easily see this space is linearly independent. Okay, and that is because of this reason. But this sends so for each ri of 4 is 1 by the given condition. So hence F is not necessarily linearly dependent, so B is correct answer. Okay, now come to the problem number 22. The same kind of problem comes in TIFR, also in this is basically the differentiation operator. That's the basically linear map that comes in JAM PYQ also. It's a very important question. So okay, so since it is a P7x to P7x, we are trying to find some fastest matrix representation that will be helpful. Okay, so P7x to P7x. So I am always interested to think linear transformation as a matrix because that will always help us to deal with. Okay, so then T of 1 is basically 1, T of x is basically x plus 1, T of x square is basically x square plus 2x, and so on. So the matrix representation is looks like this one: 1 0 0 1 1 0 0 0 2 1 0 0 0 say 3, then 1 0 and so on. So basically that all the diagonal entries are 1 1, all the diagonal entries 1, all the diagonal entries are 1. Okay, So T is clearly a surjective map because in particular it is invertible because all the diagonal entries are 1. That means this map is invertible. Okay, clearly this map is invertible because all the diagonal entries 1 means all the eigenvalues are 1. Okay, that is upper triangular matrix, right? Okay, so there exists a case as a t power k is 0. No, t power k is 0 transformation, that will imply that t is a nilpotent matrix, and nilpotent matrix means all the eigenvalues should be 0, but here all the eigenvalues are 1, so that's why it is not also hold. 1 and 2 are eigenvalue of t. Clearly you can see that 2 is not an eigenvalue of t, and if you see what is the eigenvalues of t minus I, eigenvalues of t minus I is, so all eigenvalues of t minus I is 0, because t minus I means if I see this one t if I minus identity, then all the diagonal entities become 0, and that is also an upper triangular matrix, so that means all the eigenvalues of t minus I is also 0, which implies that t minus I is nilpotent. This will imply t minus I is nilpotent, i.e. which is same as saying that t minus I power r is 0 for some r. Okay, hence this one is also done. Okay, let me check. So for the question that comes in the MSQ section, I have already uploaded that solution because that was slightly difficult question. Many students have doubts, so I have already uploaded that solution in a different video. Basically, the question number 37 video is, sorry, question number 37, and okay. So and there is a problem like question number 44. That is basically lengthy problem. I don't even think any easy idea without except just the computing. 44 is basically asking about the inverse and its entries. Okay, so what about question number 45? I think it is very easy, everybody does it, but let's check it again. So any vector in P12x looks like a0 plus a1x plus a12x to the 12. Then f of minus x is a0 minus a1x plus a12x to the 12. So fx equal to f of minus x, that will implies that 2 times a1x plus a3x plus dot 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 a11x to the 11 yeah, right, is 0. Right, that means what? Fine. So that means 2 times a1x plus a3x plus dot 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 a11x to the 11 is 0, and that means a1x plus a3x plus dot 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 a power 11x to the 11 is also 0, which will implies that a1, a3, a11 are 0 because x cube x cube x to the 11, that is basically a linearly independent set here because that is a part of basis. So their linear combination is 0, identically 0 means their coefficients are identically 0, so that means all the odd terms become additions. Okay, so that means how many terms here? There is 6 terms are here, right? Dimension of V is 13, so it is 13 minus 6 already, that is 7. But the thing is that it is also given that f of 2024 is 0, right? That means there is another one restriction plus one restriction again. Okay, that will imply dimension is 6, so answer is 6. Okay. Okay, question number 49, I'm going to solve it. This is the same problem that comes in 2022 49. Same problem, same type of problem with multiplication. That same problem. It is lengthy, but it's doable. Same problem. Jam 2022. It is just a computational problem. Okay, I'm not going to solve it. This will take some time. And the only question left is question number 50. That is a very nice problem. I'm going to say the approach. So aim is basically given by 0, 0, 0, 0, minus 1, 2, 0, 0, 0, minus 4, 0, 2, 0, 0, 0, 0, 0, 2, 0, 3, 0, 0, 0, 2, 2. So write aim as 2 times n, where n is 0, 0, 0, 0, minus half, 1, 0, 0, 0, minus 2, 0, 1, 0, 0, 0, 0, 0, 1, 0, 3 by 2, 0, 0, 0, 1, 1. Just 2 times n. Now clearly n is a companion matrix, right? N is companion matrix. Companion matrix. Right? Then what is the characteristic polynomial from this companion matrix? The characteristic polynomial is, say it should write it qx. It's basically is a matrix is called 5 cross 5, right? X to the power 5 minus x minus 3 by minus x to the power 4 minus 3 by 2x cube plus 2x plus half. Right? This is the companion matrix. Now since this is companion matrix, so say eigenvalues are x minus lambda 1 times x minus lambda 2 times x minus lambda 3. Okay, x minus lambda 2, x minus lambda 3. Fine. Since m is 2 times n, then eigenvalues of n. So m is 2 times eigenvalues of n. That means px is basically x minus 2 times lambda, x minus times lambda 2, x minus 2 times so lambda 5 here, lambda 5. Okay, now we need to find p2, right? So p2 is basically 2 minus 2 lambda 1, 2 minus 2 lambda 2, 2 minus 2 lambda 5, which is basically same as saying 2 to the power 5, 1 minus lambda 2, 1 minus lambda 5, which is same as saying that. Now take what is q1. Q1 is basically 1 minus lambda 1 times 1 minus lambda 2 times 1 minus lambda 5. This Q1 is basically given by 1 minus 1, that is 0, minus 3 by 2 plus 2 plus half. Q1 is basically given by minus 3 by 2 plus 2 plus half, plus 2 plus half. That is 1, right? Yeah, that is 1. So that means Q1 is 1. So P2 is P to the power 5 times 1, that is 32. Then P2 minus 1 is 31. That is the answer. So the matrix looks like companion matrix, but it's not like companion matrix exactly. So you just need to manipulate it to solve that. Okay, there is one question is left for question number 58. So it says that for k belongs to n, we have piecewise linear function. Okay, 0 equals to t0 less than t1, dot tk plus 1 equal to 1, and that's basically we are taking piecewise linear functions with nodes t1, sorry, t1, t2, tk. Okay, okay. So okay, that's fine. So finally we need to compute, we have v, that is real vector space, okay, of piecewise continuous linear function, of piecewise continuous linear functions with nodes 1 by 4, 1 by 2, 3 by 4. Okay, so let's see this one. This continuity property is very important here. Okay, so let's draw some picture. So this one is 1, this one is 0, so you have this one, so 1 by 4, this one 1 by 2, this one 3 by 4. Okay, so that means you are trying to take some linear functions here, right? So in case you are taking linear function, say here is the function, this is not this, some linear function is there, some linear function is there, some linear function is there, everything, right? So this is all the linear function is of the form aj plus, say, a1 plus b1t, right? All the linear functions from here and of everything, right? Also similarly here all this some of the form some aj plus bjt. So in particular what you can see here is a linear function, right? So all the function here is actually spanned by 1 comma t on this interval. On this interval it is spanned by 1 comma t, because all the functions here it looks like some scalar multiple of 1 times this is a linear function, right? Again here all the functions are determined by 1 by t, but the thing is that some 0 to 1 by 4, when you are considering 0 to 1 by 4, it's a one type of function, but since we are taking the nodes, that is a different type of function. Okay, so in particular we have to see that, see it is actually different. So here is basis t and here is basis t actually different, because we have a node there. That means that, that means not just like the function is just like this type always. Okay, there may be some function like this and then that. Okay, this then that. Okay, something like that. So in particular you can see that there is so for this portion, I'm trying to for this portion, for this portion for this portion it is spanned by these two. Okay, for this portion it is also spanned by these two. For this portion it is also spanned by this, and for this portion it's also spanned by this, right? Okay, but the thing is that there is some extra condition we need. Why? Because we need continuity, right? So there might be some function, if I want to draw it properly here. Okay, so there might be some function here which is say this and then this is also piecewise linear, but the thing is that this is not continuous at point 3 by 4, so we need continuity at 3 by 4, right? So we need continuity at 1 by 4, we need continuity at 1 by 2, and we need continuity at 3 by 4. 0 and 1 is automatically hold for the first part, so we don't need anything there, because that is part of this, that is part of that, but we need continuity at the nodes at the node points, right? So in particular any elements here should satisfy that. Say for this part, say if I write it as box 1, if I write it as box 2, if I write it as box 3, if I write it as box 4, say any element of box 1 should satisfy that. For box 1 I'm just giving an example. For box 1 and box 2, that should satisfy that f of 1 by 4 is equal to g of 1 by 4. I mean, if this section is z, this section f, then it should satisfy. That means we need to, so we have another restriction. Again, we have a restriction at 1 by 2. Again, we have a restriction at 3 by 4. Okay. So in particular, we have three restriction. We have three restrictions. That means the dimension is actually 8 minus 3, that is 5, because here we need to span the vectors. We need this one is basis for this zone, this one is basis for this zone, this one is basis for this zone, and this one is basis for this zone. So that means we need 8 vectors to span the whole space, okay, which is in fact a basis. But the thing is that then if it is asking about just linear functions with nodes, that then the dimension is 8. But since it is asking about continuous linear functions, that means there is some extra condition is already imposed there. So these are the extra condition. You need the continuity requirement. I think if you see the 2021 paper, there is something related to the polynomial case, because there is defined to polynomials piecewisely, okay, and then we require some continuity in the joint section. 2021 there is a similar kind of problem. Okay, I think that was in MCQ. I don't recall. That maybe in MSQ, but that is the same type of problem. So idea is the same. Okay, so hence dimension is 5. Okay. Okay, so that's all for linear algebra. Thank you. If you have any doubt, you can comment. Okay, thank you.